This is a talk about concept maps using C++23 library tech. Now, by that I mean I'm going to be using a lot of language features, but implemented as library stuff, no language extensions, although there's some stuff that we might eventually be able to shoehorn into the language. C++ OX concepts, if you're that old, had a feature called concept maps. Allowed a set of functions, types, template definitions be associated with the concept, and the map to be specialized for types that meet the concept. Allowed for open extension of a concept. You could say, oh, this is how my thing meets that concept's requirements. And a definition could be provided that allows an algorithm operate in terms of the API a concept presents. The algorithm wants to work in its domain, and the map defines how those operations are implemented for a particular type, which should be working in its domain, not the domain of the concept. If you've ever had to implement like transform for one of your types, you know what I'm talking about. There's no good reason for that except that's what the algorithms want. This is also very similar to how Haskell's type class works. We lost this when we got Concepts-Lite. Why? It's like basically, why am I doing this? Because don't know if you should. It's a need to know if I could first before even talking about this. So some of the alternatives that are out there already, we can do provide a virtual interface. We can provide an adapter that wraps up your type and provides the thing. This is all classic technology. You could provide a collection of customization point objects that are all the things that your algorithm needs to talk through. All of these are a little bit unsatisfying or have overhead, and they're harder to support. Just to give you a feeling of what I'm aiming for and what we lost, here's an example from OX concepts. We're going to start with, we've got a student record. This is very boring. And we've got a concept equality comparable from back in the days when we were capitalizing concepts. We want to explain how to say equality comparable for our student record. And so our operator equal takes two student records, compares if their IDs are equal and returns that. It's nothing complicated here. But it does mean that it's like you don't, unless you need it for other reasons, you didn't have to put equal in your interface. Things that need equal should say, I want an equality comparable, and they would get it from this. You can also allow associated types, so you could provide a type def for for a binary function and say that the result type is an int and get that out later. So why didn't we get them? And let's not go there. It's like, we can maybe talk at the bar later, but this is still contentious about what exactly happened and when. This got pulled at pretty much the last minute in C++11 and with a lot of contention about why did we need this? Can we do concepts without it? Is it going to confuse users, etc.? So let's take a look at what the state of the art in this space is right now. And that's pretty much Rust traits. Rust has a trait, partial EQ. It provides an EQ and an NE. It's like where NE is not equal and defined by default in terms of EQ. So, and works pretty much like you would expect. This is in some ways also understood by the language, traits part obviously, but some of the core traits, the language cooperates with you on in using that. C++ customization point object, CPOs. This is a little more verbose. Not too complicated, but it's like, if we've got a has EQ, you can get an EQ function object, have any that returns in terms of the EQ, check to see if it has an any, provide the any function. This will all be in a hidden namespace because this is just machinery. And this is what you'd end up exposing to your users. Your namespace, you'd pull in the function objects, pull in an instance of the EQ function, the any function, and expose your concept. This is from Barry Revson's blog post from a few years ago, 2020. It's like why tag invoke was not the solution he was wanting. It's like where he was also saying, well, tag invoke may be better than this, but like it's still not what we're really looking for. And I think people are probably aware that we pulled tag invoke out of senders receivers now. It's like over a lot of the concerns that he was raising here. So what do I want out of a solution? It's like, I want it tied to the type system. It's like, I want to be able to say for my type or a set of types that have some relationship that I want to talk about, how do I use them in terms of my concept? I like types. I like the type system giving me guarantees. I like the type system telling me when I've got something wrong. The downside for this, though, is that, at least as how I'm doing this, there can be only one for a type or a set of types, whatever the concept we're matching on. So we could run into the same kinds of problems of like, what if you provided an operator angle for vector? And they do too, because everyone wants one for their tests now. And we now have a solution format that just prints out sensible for us how to print out a vector. But it's a common problem for people to define little utilities for themselves on other people's types that then leak out and eventually collide. And if you're lucky, you get some kind of linker error. If you're unlucky, you get the wrong one when you wanted it. So, now I'd also like for this to be automatable. It's like something that it's like I could check or write a tool that helps me inject these things. I haven't done anything towards automating it, but like this is, at least in the usage side, is pretty mechanical. So we'll get to that. We want zero overhead because it's C++. That means in particular, we don't want any virtual calls here. And we don't want any type erasure that's going to make it more expensive, like effectively creating a virtual function by some other mechanism. So one of the things I would ask myself, okay, Haskell's done this for a while. What actually are they doing when you define a type class and say, my function uses this type class? It basically just adds a record of whatever you said the type class implementation was, the instance for it that defines the operation, and then like hides the record and does it automatically. Basically, lifting the names of those members of the type class into the scope of your function. And it's like, I can't quite do that, but we can come pretty close. So it's like, so we want some kind of mechanism of type-based lookup. And it's like, so what can we do that allows me to look up some object by way of some types? Templates. This is actually very, very good at this. And additional requirement it's like, is I want to avoid ADL. If we can, we've learned that it's like ADL is great when you really want it. When you don't want it, someone ends up getting unexpected function calls, the overload they did not want, and then the compiler errors, if you get them, are horrendous. It's like not great user experience. So we want object lookup. We want to look up rather than overload lookup. So what I can do, variable template. And there's been a lot of improvement, both in the specification and the capabilities of the languages and what compilers actually allow you to do. It's like, I don't have a whole list of this. I just know that it's like when I tried with earlier compilers, they didn't work for various reasons. They've become a lot more powerful. In particular, we can have entirely distinct specializations. Your variable template does not have to be related to any of the other definitions or the base definition any more than any other template. The one thing that is slightly unfortunate, you do have to provide something for the base template definition. Just mechanically, you've got to have something there. You can't just say, there is a variable template that takes these, you've got to define some variable. I've been using false type because it gives kind of indicative error message if you arrive at false type or test to see if things are there, that it's like, no, they're not, this is not what you were looking for. Step towards an implementation. Looking at partial equality, it's like requires that remove reference T. This is getting us a T to examine in our requires clause. That the variable template that I'm going to be defining in a bit we can call EQ on it with our type, and it returns a bool or something that's very Boolean-ish, and that I can call any on it. Making the assumption that there will be something partial EQT that I can ask this question of. So what is this going to look like? Inline variable object, very much like we define in Nebeloids. So we've got a const expr inline auto partial EQ that is a variable template. In this case, I've got a useful default that you can pick, that you could pick up from elsewhere. If there is no default, I've been using false type. It's like an empty struct might be a useful thing here, but then something that tells you you've not reached it. But for EQ, there are useful defaults to provide. So like default implementation, we've got our partial EQ default T. We define EQ and NE for it. Define them in terms of equal, equal, and not equal. because those are just built into how C++ looks at things. And this is not terribly surprising, or I mean, it's like that. At least in my opinion, the interesting thing about all of this is not any particular thing here. It's that I can pull them together to do something useful. So we define an object for this. It's like our new HasEq. It's like basically we require a tconst reference v that its operator equal returns a bool. Since this isn't actually invoked, it doesn't matter that those are the same object. This is just concepts are purely syntactic. No code get executed here, so you don't have to worry. It's like, oh, maybe it doesn't work if I compare. This is only testing self-comparison or something. This is just like, you need a t of whatever to call operator equal on. It's doing a little better with what I can provide in a bit. Let me switch back, but what I want to talk about, Zach.
Can we go back to the previous slide? I'm just curious.
Maybe.
There's a reason why you spelled out operator double equals instead of just writing v double equals v. Was there a particular reason, or you were avoiding rewrite rules, or something?
It's like not any particular reason. I didn't spend a lot of time here. It's like I wrote something that worked, and it's like moved on for slideware.
So HasEq is for every type that can be checked for equality with other object of the same type. And then in the previous slide, you allow different types of objects.
Possibly. It's like this one. Okay. I guess that would be back here. No, those are on the same one.
No.
Go forward a couple slides.
Forward. Just go forward a little bit. One more, I guess. Yeah, so here the LHS and RHS are.
Oh no, okay. Types. This is a default implementation. Yeah, I'm allowing. Yeah, it's like you could confuse this. It's like,
so left-hand side,
I'll add a
right-hand
test.
side can be different types, but each of them has to be equality comparable to itself.
Yeah, it's
You're
like
not checking
okay,
the equality comparable to the other one. That should be cleaned up.
It can be cleaned up. It worked in the cases I was testing.
Yes.
I want to talk a bit about monoid, which is one of the concepts that I actually have real use for. It was kind of driving this, and if there's time at the end, I'll show some of the code where I'm really using some of the features of monoid. Monoid's a little bit more than you think. Monoid's a type with an associative binary operation, and that operation's closed. The op always gives you something that is in the type, and there's an identity element. So maybe there's not a lot more than you think about it. This does turn out to be fairly rich in what it gives you for those small collection of things. Looking at it in mathese, we've got sum operation from m to m giving you an m that it's associative. We can do the operations in either order. There's some identity element that such that for all m, it's both a left and a right identity when you do under that particular operation. If instead of op form with that circle plus, we use functions, we've got function, looks the same. It's like the function calls nest, and it's like when we call our function with our identity element is either the first or second, you get the other element that you were providing. Similarity for those nested functions to left and right fold is not an accident. This is what makes folds work. in the general case. It's like this covers all things like, okay, what if I'm folding over nothing there? Okay, well you get the default element out of it. It's like, how do I know that I can do things in parallel and assemble them later? The associativeness gives you that. So it's like, and what turns out to be the case, often your operation ends up preserving some information about the elements that you're giving it, and that's useful. And that's why we fold things up often. So core functions for monoid, empty, which returns an m, which has a surprising. This is Haskell form. I'm stealing a bunch from Haskell not because I love Haskell so much. I like it, but it is the language that's been used for algorithm research for like the last 30 years. It's like having a reading knowledge of Haskell is pretty much necessary for reading any of the current literature. It's like, and then figuring out how to translate it into whatever you're trying to implement. But empty turns out to be equivalent to concat, the empty list. So concat, one of the other operations on monoid, takes your list of m's and turns it into one m. This is equivalent to fold, append, empty, where append is your operation. It's like where we've got an m and an m and it returns an m. It's like, and that's your op. Like, note that that's self-referential. It's like, so essentially you have to provide like a couple of these, not all three. You can provide all three if like, oh, I've got a much better way of doing all of them than the defaults. It turns out like for monoid, you probably just want to define op and empty and let it pick up define concat on its own. But occasionally it's like, oh, no, actually for my types, concat is much more natural. And it's like, I want the other things to be pulled out of it. And the self-referential is common, and the property that you only have to define some subset of them. It shows up even more strongly in monad, but I won't be really talking about monad.
Sorry, what does the square bracket mean? What does the square bracket mean?
List. And the list with nothing in it is empty list.
Yeah.
That's like,
You are talking about monad, Steve. It's a monad.
Yeah, list is a monad. Everything's a monad. It's like when someone tells you something is a monad, this is not surprising. It's like finding out something is Turing complete. It's like, oh no, everything's Turing complete. You can do addition, you're probably Turing complete. So, from the Haskell prelude, it's like, because if I'm stealing things, I might as well look at their definitions. This is how they define the core functions. Some of them, these names have a bunch of history behind them. They admit these probably aren't the greatest names, but it would break too much to change them at this point. It's a minimum set is defining empty concat. Plus your operation. But it's a we write this in C++. What are requirements for some type for T and M? It's like an identity that'll be the same as M, or I'm using empty view because I just needed a range and I don't need to get anything else out to operate on the range then. If we concat over the range, we get one of the m's out. Okay, that's sort of one side of it. This would be like, this is like what I'd need to implement the instance of the variable template. It's like, also want to talk a bit about what it looks like on the other side, implementing the thing that is the concept map. They're isolated from each other. There's no requirement to implement them this way. You could do it directly however you want, but it's like, I wanted to provide at least some nice features, like making it easy to provide the like 2 out of 3 things that I need. The map for a monoid requires requirements are the previous slide with some impl type that provides a value type. We're going to inherit from the impl, and I'm basically type checking the impl that you provide, and then using it to provide any of the other operations. So yeah, we've got sort of a CRTP here and deducing this because this thing provides all the operations. So if I ask it, do you provide the monoid requirements? It's going to say yes, even if like my implementation didn't, and they're all co-recursive now. Identity, I've got a put string here because when I was writing this, I wanted to know that I'm calling the thing that I think I'm calling. It's like there's enough moving parts where it's like, wait, no, it's calling like the provided one when I really expected it to be calling the implementation provided one, and it's like, okay, what's going on here? So it's like concat the empty view with one of those horrible things, but it's like basically empty view doesn't require anything because it doesn't actually instantiate any of this stuff. So it's like, this is an empty view. It's like an empty list of M's. No M's are involved in making one. So and then we can use the concat operator provided by the derived type to get one of these. Now, as I said, you probably in practice would define identity yourself, and this wouldn't come in, but concat, we're going to do a right fold with the identity type, which gives you your base element, and just do the operation for our monoid on that fold. And this will concatenate all the things together. And then whatever our op is, we return self op because we might have provided. This just bounces into the implementation basically. So yeah, I'm using like deducing this and CRTP because I'm using them for 2 slightly different reasons. So I want to look at your implementation to make sure it actually meets the requirements, that it's providing the operations that we need. And CRTP because we want the self parameter to be the static visible type of the derived type, so we get to the right operation if you're using the defaulted operations that the map gives you. It's because we want to constrain the required implementation. We want to use the derived version, which has all of the operations. So here's the plus monoid over some type M, like if that's an int, this gives you the most basic monoid. Identity is just 0. you add 0 to a number, you get that number back on either side. And yeah, operation is just plus. So it's like this. It's like, and then from this we can derive these two provide concat through the map machinery. So yeah, it's like so we want to say that our plus monoid map we're going to inherit from the monoid on plus m, and then pull identity and op into scope, so they're visible for the operations for concat to use. It's like this is a little more. Chris?
Is there any reason why it's not just a type def? Can you take this off?
Yeah, could you?
Is there any reason why it's not a type def and is instead a struct?
Oh, so I can make an instance of it.
Cool, thanks.
But,
There's another reason.
Okay.
You need to hide monoids versions of the stuff that you provided.
okay, yeah, that's it. Good. Okay, so it's like we can provide some concrete instances here. Our base type for a monoid's false type because like random things are not monoids, but int, long, char, all find to be plus monoids. For exposition purposes, it's like, could I do this with concat? Like in theory, I'm saying I could. It's like, I'm not saying this is a great way to do this, but it's like, let's say for string, I want to define all the operation in terms of concat instead. So I'm going to have our operation, which is take the string, put the other string next to it. It's like plus on strings is, it's actually reasonable to have the string concatenation be plus for basically this reason. But it's like, this is just taking the strings together. And we define it in terms of concat. So if we've got a range of strings, the result of this is just string, 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 all of the elements coming out as one big long string.
Is there a reason why you didn't constrain range to be an actual range? It's just a type
No.
thing there.
It's like, they make the slide extra noisy.
Okay.
So for integers, for example, the plus operation is a monoid, but also like the maximum operation is a monoid. So
Yes, actually, I will get to that. And yeah, it is kind of a problem for things like numbers, which are really rich, and there's like a lot of different monoids you can define on them. What I've ended up, it's like, this is another case where it'd be nice to have some kind of strong type def where I could like just say, for ints, give me a plus, a min, a max, and it's like that. Do all the things int does, including arithmetic, but they are distinct types. We don't have that. It's like been proposed a few times. There's library machinery to do in various ways to do it. None of them have been quite good enough to cover everyone's use cases. So it's like now everyone gets to write their own. So okay, we can get an instance of string monoid map based on the prior implementation of string monoid, and this will provide, and we're using the op and concat that we defined, and we get empty for free, which will return the empty string when it folds over the list of no things in the list.
But it's not associative.
Yeah, it is.
Yeah, it is.
strings, congrats.
It's not commutative, but it is associative.
It's not commutative, but yeah, it's like you can if you've got three of them, you can do the do these or this one, or you can do these two or that one. It's like, and it's the same.
Unless you have a question.
Right.
You're right.
Keeping me on my toes, though. I'm like, oh, wait. Here's some simple uses. We're just some exercising of this that it's like, so I've got a generic test function. I don't remember why it's P, but whatever. So like we find the monoid concept map for the type that's coming in, and call identity op and concat on these, and get the expected things out. I'm making an assumption that I can get conversion from integers to whatever these are, but this is slideware to give some flavor.
Things like string where you allocate, would you want to be this straightforward, or would you want to do a more notional sort of operation?
You might want to do something more clever there with their allocations, right, where you figure out how big things are and do the work ahead of time.
But calculating the allocated thing, and that's the actual actions.
Yeah, but this is, it's like, since we're treating these all as values, yeah, it's like, you could build up a massive lazy thing of like strings and instantiate several thousand of them, which promptly get discarded. But it's like,
so Haskell gets the lazy for free, but we would have to find out how to model that or something.
Yeah. Well, it's like ranges already give us laziness, and senders receivers have laziness built in. We should probably think about providing some more generic. It's like, call this function, only don't call it until I ask for the value. It's like, these are fairly simple. It's like, the problem is they're almost too simple, where it's like, okay, do we spend time getting these into the standard, or do we expect you to spend an hour writing it yourself? Like, there's a lot of things we could put in the standard that we're like, no, you're a C++ program, just write it. But, no one else is sharing your whatever that is, so it's not going to be vocabulary. It's just notional. You should know how to do some things. It's like, so some simple cases, like, you're going to run the test for int, the test on long, test on char, run those functions. We're going to do a similar thing on the string definition, but here it's like, because I can't convert from by default from integers to strings, providing strings to work with. But this does basically the same kind of thing. And note that like the type of the map, like, is mostly invisible. You don't really care about this. And it's like, and putting that in that monoid concept map at the beginning of your function is pretty mechanical too. Results, it's like when we call the test int, it's going to call the plus the identity that I defined and the op I defined, and then it calls the concat that's being synthesized by monoid, and then calls the op that I defined 4 times. Actually, this is actual results from compiling the other bits of code and machinery to stuff it into my slides. Long works the same way, which, not surprising, but it's like, okay, I've got some test cases here. It's the car works the same way. It's a string. That other test works differently because it's like I'm calling my identity and it's synthesizing a bunch of the other stuff for me. But string monoid op forwards to op, it's which in this case isn't printing out anything. Now one of the reasons I'm interested in monoid is because they turn out to be really useful for putting them in trees, for tagging the data in a tree. It's like foldable, it's like sequences are basic foldable, and we usually think about applying monoids to ranges and folding them up. You can generalize that to trees and get some very useful pieces of machinery out of that. Folding is very much tied into range-like things, but it can and is generalizable to things that are more just traversable and not necessarily specifically foldable. Monoids are still critical for that because that's what gives you the property that it's like, I don't care so much which way I order these things, they're the same. What's useful for a monoid is providing a summary for a data in a tree. You can use a tree to provide indexed access or search access or priority queue access into some range that's sitting there. And it's like, so it's not the kind of binary tree where you've got data laid out like in the tree. Data's all at the edges, and your tree just spans the whole thing. Like B-tree indexes work this way, and a lot of times it's common to do this where it's like, I want to provide several different indexes on the same data. And you share the data and provide the different indexes that all refer to your data. So the summary type's monoidal. The nodes can hold summaries, caching that of all of the data below them. So you can have, it's like, and if finger trees were invented or discovered fairly recently in the early 2000s. It's like, but the core data type provides log n bounded simulation of priority queues, indexed access, sequential access, it's like, and a bunch of other things. It's a ridiculously general purpose thing, and much of the flexibility comes from the monoidal tags that are used inside it and composed. They're also fairly complicated. There's a lot of machinery in them to keep them like self-balancing when you do the inserts and et cetera, which, and providing like bounded guarantees about like if I split the tree or concatenate two trees or want to pull off data from the left or right, maintaining all of that. And a lot of that complexity obscures how simple some of the other operations are. So yeah, the same techniques can be provided, can be done for other simpler trees at additional cost. Like, okay, so your tree's not balanced, so now you might have just a very, very expensive singly linked list because it's all down one side or all down the other. Like for real applications, use a good data structure. If you're trying to understand how it works, that's less important. I have the paper number. P3200 will eventually have a proposal for finger trees and a bunch of algorithms that go with that. I don't know if the monoid technique I'm showing here will survive to that, but like this shows up in enough places. Oh, another useful thing about it is that it's a so-called functional data structure. So operations on it return, like if you insert into the tree, you still have the old tree that everyone else is looking at, and the result of the new tree is sharing all of the things with it. It's like, it's, so copy of the tree does not need to be a full deep copy, or it's like inserting a new top level node just as like, oh, okay, here you're just pointing at the old tree, but we've got only enough modification of the nodes to distinguish like the operations. In particular, this gets used in string-ish operations in pretty much every other language right now, because most Unicode algorithms spend an inordinate amount of time moving stuff in the middle, one over or one back, or deleting like a couple of octets. And despite vector and modern CPUs being pretty good at this, this is one of the cases where it's like it just gets bad. Your 1 meg string where you're trying to do normalization in the middle because you attach two of them. You're doing all this work in the middle, and there are effects when you normalize both before and after you concatenate them, and you spend all this time, if you do it with just a vector, moving this large block of data over this much, and then over this much, and then over this much. And then if it's editable, someone will say, okay, replace this word with this other word. It's like, okay, do that work. And then it's like, and then renormalize it. And you spend all this time moving data around. Enough that it's like, even though moving a meg of cars is pretty cheap, it's still cheaper not to do it. Other people have measured this. It's like, it's not just because this is cool. So what I've got, it's like that I've been using for experiments on this kind of thing. It's basically a fringe tree. It's like it doesn't do self-balancing, but all the data is in the leaves. It's like branches just hold a left or right subtree, where that tree might be a leaf, a branch, or an empty node. So I can show you some of that code, so we can get a sort of feeling for what this looks like. If I can find. Hold on.
Is that a GitHub link? Steve, is that a github.com user?
Yeah, that's my username on github.com, and the branch is where I've been doing this work. Let me oh, I see what I've got to do here. Oh, okay. Now no. Internal confusion. My computer has decided that screen is over here, and I keep trying to go this way.
I was having that problem yesterday.
It's like first world problems, but
I have 4 screens. Where are they?
These are all the tests I was running earlier today. Okay, so it's like, yeah, this is the code that I was doing for showing in the presentation itself, how things get defined. Let me show you some of the code that I was using for the fringe tree. And the heart of what it works on, is, as well as for finger tree, there's a concept in type class measured, which says I've got a way from getting from my data to some measurement type that is monoidal. The different ways you can do measurement are what gives you the power for the tree data structure to model so many other things. One of the primitive ones, which for no good reason I'm using for the base int type of monoid, is basically counting how many things there are in it. So That's why it's returning 1. So it's like, so for whatever value you give it, it's asking how many things are this? And it's always 1. The monoid though adds those up because it's just the normal integer plus monoid. So if a branch has two leaves below it, each of those has measure 1, and the branch has measure 2. And you can say, well, now I know how many elements there are just looking at that, and I can use that to index into the tree and into the elements in log n time, since I know where I am. If I need to find the 5th element and there are only 4 in it, I can tell you right away that it's like looking at the cache data that you've gone off the end. If there are enough, I can then look at the left and right and see, oh, okay, there are 5 elements. There's 1 on the left and 4 on the right, so I've got to go to the right and descend down and find that point. It's like that's fairly simple to implement. What this did remind me, though, as I was implementing it, because I needed this to fix a bug I discovered on Tuesday, it's like, one of the interesting things about concepts is this is a concept that is defining a relationship between types. It's not a property of either the value or the monoid. It's saying that there's a function measure which gets me from these things to that thing. And that's true of a lot of concepts. It's like, and it's why we can't just put a lot of things into the type system directly. Even though it's like concepts as predicates on types are very useful to also, because that can tell you, oh, you've got all the operations that I expect you to have. And I can hang off some semantic requirements. So it's like, oh, those operations have to be well behaved in some ways. So I'm using the same machinery that I was talking about before to define the operation match, where the operation is measure that a measured value and tag type need to provide. Fringe tree is made up of it's like branch, leaf, or empty, and tree. Just I'm forward declaring them, so I've got the names. Branch is a shared pointer to a left tree and a right tree. It's like by default, those are all set to 0 initialization, and it's like this pretty much behaves the way that you might expect. It's like the one other thing that led me to hold off on proposing this, because this pretty much inherently uses variant types, and you want to expose being able to operate on the elements of the variants to users. Pattern matching. Yeah, I was not going to try and propose this and inflict visit on every user. It's like, I'm doing it, it's too painful, no one else should have to do that. It's like pattern matching and destructuring the kinds of things is really straightforward. It's like, yeah, so it's like, turns out the tree itself is measurable, and basically just you get the tag values, which is holding the summarized data for each of them. When we're constructing the, yeah, that's where I end up. Okay, that's the visit bits and pieces. Okay, here's the, like, so when I'm constructing a branch out of a left tree and a right tree, we get the monoid for our tag type, where the tag is how we're annotating the data in the tree, and we call the monoid op on the left tag and the right tag, and then construct a branch out of that and return the branch. The underbar types are just like aliases to the, using aliases for the much longer ones that have the tag and value template defined. And it's like, we do similar things here. And then there's a bunch of operations that is like defined as CPOs that basically all operate by passing a visitor object down the tree, and it picks the branch or empty or leaf operation to do as it accumulates up. It's like, and we can do a bunch of operations. It's like, oh yeah, this was for demo purposes, but I can print it into a dot graph and get the picture out, which was helpful for me in trying to visualize what some of these operations do. It's like, so a bunch of mess here. It's like, and then we want to be able to, prepend to trees, append trees, concatenate them together. So I can view them from the left or right. And basically, this was an exercise in basically reading someone else's paper and going, okay, I have to translate from research paper ease into C++, but it's all fairly mechanical, which gives me optimism for being able to take good existing implementations of finger tree and translating them into C++. The shared pointers aren't exposed in the interface, but it's like, at least when I was measuring it, you might be able to do a little bit better by writing some internal thing that managed them in a shared fashion, but shared pointer is pretty good. It's hard to do significantly better than shared pointer already is without making your own class of mistakes that shared pointer has learned not to do. Various ways of treating trees as lists. There are, although we didn't get them because he didn't propose them at the time, tree operations in the original STL proposal. As Gaspar reminded me, in Elements of Programming, Stepanov does have worked out tree abstractions where it's like more than just iterating through. It's like, I want to actually go left or right or up. And it's like, this extends, and you can then generalize tree notional things to the algorithms that operate them. And there are a lot of interesting algorithms. And trees are one of the cases where I think it's unfortunate that we leave programmers to implement their own trees all the time. It's like we do have a couple of trees in the standard library. We hide them so well that it's like they're not usable as trees. Let's see, this is pretty much, the end of it. You can see a little bit in tapped in the wrong spot. My test cases, I've got a test case version of min, where I'm applying it. Okay, I'm not going to go use up all the time unless
an interesting application of concept maps, though. Like, one of the downsides of trees and graph type algorithms is that we're doing real engineering, so like the locality of data and the preference of data actually does matter, and maybe that's why we don't see more trees. But you could say, well, I'm implementing this interface for an edge major tree where we like.
But on the other hand, things like AST, every compiler implements that. It's it's classic tree technology. There are actual pointers being chased around, and it'd be. Compilers do have algorithms that they apply to their AST, but it's like we could probably do better. That it's like, okay, we can make it easy to apply this algorithm to your tree if you just make it look enough like this, provide the hooks that we need. The same way that we've now made anything that looks remotely range-like, you can pass it to the range algorithms. So, yeah, so just for, here's, instead of, here, the min monoid, this one's actually a bit interesting. This allows us to implement priority queues with this. Where our base type is the minimum, our type for the empty, the identity, is the minimum numeric value. It's like, if you compare if like the minimum value is less than your value, it's like, unless you are also the minimum value, you get your value out. So these sort of, and your operation is just less than then. So if we use a min, as the monoid type on this tree, we can get priority queues out of it. Instead of searching for size, we can search for something with the priority that we want. Whatever the lowest priority is, we get it out quickly. It's like, this is a little bit noisy to do. This you probably need no matter what, if you're trying to implement some monoidal type. The overhead is mostly here, where it's like, okay, here's my definition of identity and op, and here's integrating it with the measured concept, going from arbitrary data to a min and for it, or we just assume we can construct out of the underlying data type into our new data type, into the min type. And here's a declaration for the measured concept map and the monoid concept map. The measured concept map I actually was just adding this morning, and it's closely related to the bug I found. Once I said, what if I tried applying the techniques I'm talking about to this problem? It's like the compiler said, oh, you need this here and you didn't provide me this, do that. And it's like, okay, I did that. And then it's like, okay, all the tests passed now. It's like, okay, that's good.
So if my name wasn't Steve Downey, would that error message say the same thing?
Yeah, because the error message was actually false type doesn't have measured on it. You're trying to call that here. I'm like, oh.
Okay, that's good.
So it unwound the thing. That all of this machinery is very, very transparent to the compiler and vanishes during compilation. There's no magic that it gets confused by. It's like the results are the assembly that you would have written by hand if you still wrote assembly by hand. Okay, are there other questions? Sure.
Okay. So if I understand correctly, a concept map for some concept in some type T is a specialization of the concept for T, which actually is derived from type T and either exposes with using declarations or getting using your mechanisms.
Yeah, it's essentially a bridge. It's like, at least in all the times I've been doing this so far, the definitions are like one line of code. It's glue code to get you from the domain of the algorithm to the domain of your type.
Yeah. So my question is, why derive from class T and not, for example, have a member of that type, or maybe a reference or pointer to that type? Can you talk a little bit about that?
Partly it's I wanted to make sure to avoid ADL. It's like so if I'm looking for the monoid that I'm interested in, I just want to find it by name and get that one. Similar to how we work with CPOs, that it's like you don't want these operations to end up involved in overload resolution past that point. Guess what is it?
Yeah, I wanted to say that the way you compose these three layers is pretty brilliant. I do have an idea of how you could enable int plus and int times as separate monoids though. So if you treat...
That's a big part of why I'm presenting this, because it's like, oh, I think this might be useful. I need to talk to other people so that they can say, oh, either I'm wrong, which is very possible, because it's like, I did it, I'm excited. But it's like, oh, there's other ways of doing this, we could extend it. In particular, I agree, it's a problem to be able to have so much noise to say, I want the plus monoid on int, I also want the multiplication monoid on int, I want the counting, I want the min, I want max, and it's like, and they all look exactly the same except for the operation.
So it's not that hard. Like if you start thinking of the variable template you defined for concept map as the default one.
Ah, okay.
And take it as a defaulted NTTP.
Ah.
Then you infer the type anyway, you infer the concept map, but the user gets to replace it.
Okay, yeah, sure. One more level of indirection solves problems.
Yeah, but you don't get any more syntax
Except
in
too
the
many
cases
levels of
that you
indirection.
showed, and
But I can swap in different sets of stuff
whatever
then.
you want.
Yeah. Some fun homework. Other questions? Right?
Are there a lot of applications for more bread and butter specializations, like serializations and things like that?
Yeah, it's like it's a chronic problem for it's like using an algorithm. We end up polluting the names of our business types with all of these CSE names of things that we want to be only because we want to be able to provide it to some algorithm. And it's like with this, you still have to put those names somewhere, but they're not sitting there in your types interface, making the interface a lot messier. It's like separation of concerns without any particular more overhead. 'Cause it's like the definitions that are split off into the map are the ones you would have written as exposing these names on your type anyway, basically. It's just now there's two things for it instead of one.
So would you choose to, let's combine things. Would you choose to like have reflective enums implemented in terms of something like this, or would you want something, or would you have a more hand-rolled approach?
A lot of this stuff is really mechanical. It's like if it works out enough, this is the kind of thing that compilers could really do for you too. It's like with maybe a little bit of a hint, but it's like, I want you to build one of these things for me out of these operations, and it's like, I can stamp one of those out for you, no problem.
So like the as if lambda kind of like is basically a function object under the hood kind of thing? Or,
yeah, it's like, not the same, but like sort of analogous. So it's like, I know how to build a vtable. I don't have to. It's like, you've given me the list of operations. I can stick them into these. With some syntactic sugar, you could convince the compiler to do this same thing and even expose the variable template for you without so much noise. I am not proposing that without a lot more demonstration that this is actually useful. Also, it's like, and Gaspar actually showed me some things that he's got in the pipeline that reduce the syntactic noise of a lot of this also, that are also generally useful.
We get rid of the forwarding function, and that's nice. P2825, P2826.
Yeah, it's like one of the things is you've got basically a way of injecting a name into overload resolution, and then if it's selected, it's like, really just call this. Like, and it's like, you said it was straightforward to implement. It's like, it sounds like it's straightforward to implement. It's like, it's just like, oh, yeah, I can call that instead of this. That's easy. It's like the trickier bit was the associated thing where it's getting the declared type out of an expression. So it's like
the decal call paper, that one's actually easier to implement. you literally follow the built-in constant p implementation and change 3 things.
Okay. But yeah, it's like it's sort of analogous to decal val. It's like decal call. Give me the thing that this would be, that this expression's equivalent to, and it's like it could remove a lot of noise from this. Brett.
Did I hear you right? You said you implemented this all with C++20 language constructs?
23.
23 language constructs.
Yeah.
Okay.
It's like there's no compiler magic. It's like could probably even strip it down to C++20, but it's like
it seems like an application for this would be a more modern test framework because there's a lot of customization points in one of those, right? Where it's like self-registration.
Oh yeah, probably for it's like it's like adapting matchers, for example, is probably a good would be a good use for this.
Yeah.
So,
get rid of get rid of a lot of that macro nonsense.
like, yeah, between that and this, something like this and reflection, it's like we could make the test frameworks a lot more just C++. So, because yeah, it's like there's certainly a lot of like hidden ugliness in most test frameworks macros. But, anything else? Anyone else questions? Okay, in which case, thank you very much.